Good afternoon, students. Let us start the analog electronic circuits class. We are right now discussing the low frequency and high frequency response of the amplifier circuits. So, yesterday we had finished the low frequency analysis of BJT and FET amplifiers. Now, before we have to start this high frequency analysis, as I had told yesterday, there is a parasitic capacitance between base to collector region or between gate to drain region, and unless that parasitic capacitance is modeled in our transistors modeling, we will not be able to proceed further. Now, for that purpose, one scientist called Miller had derived some expressions about this particular capacitance. That is why now this capacitance is called as a Miller effect capacitance. In the last class, I had written that particular diagram and I had shown you that how the base to collector junction is remaining reverse biased, and because of which there is a depletion capacitance, and that capacitance becomes predominant in high frequencies also. Because you already know that X equals 1 over 2 pi Fc. When F is very high, Xc will be low. When Xc becomes lower, natural high frequencies from the base will be gradually transported, or they will be connected to the collector also. What we exactly visualize is when the signal is given to the base, when the transistor is in the quiescent conditions, it will gradually switch on or switch off towards cutoff and saturation, and that is how we visualize that when the transistor is switching, it is producing an amplified version of the input. But now, when there is a parasitic capacitance between base and collector, it is going to affect the switching of the transistor itself, because instead of causing change in the base current, now the signal may get directly coupled to the collector by means of this internal capacitance. That way the transistor may not switch properly at all when the input is of very high frequency. So, to analyze this high frequency analysis, now we have a method called Miller effect capacitance. You can see this particular block diagram where I have written the amplifier's block where voltage gain is given by AV equals V0 by Vi, and I have already indicated Ri as input resistance, Zi as input impedance, and Ii as input current. First, let us find out this Miller's effect considering the input side. Now, looking at the input circuitry, you can visualize that out of the total input current, part of the current goes into the amplifier. Now, remaining part of the current is going through this parasitic capacitance. That means between base and collector, there is that junction, and the CF is indicated as that particular parasitic capacitance. The reason why we have written CF is, it is as a feedback capacitance. That means output can be coming back to input also. That way it is written. Otherwise, in our amplifier's case, it need not be feedback. It can be input to output also, or it can be output input also, in both ways, because the capacitor is going to pass AC signals from both directions, right? So now, whatever is II, that is the AC current, and I1 is also AC current, I2 is also AC current. Otherwise, you may think that how current can pass through the capacitance. We are discussing the AC analysis of the amplifier itself. For that matter, all these currents and voltages are expressed in terms of AC. So now, let us proceed with the analysis of such circuitry. What we want now is, when the CF is there, how can we apply KVL now? Now, for this circuit, we cannot apply KVL. We can apply KVL at the input side. Let me annotate. We can apply KVL at the input side, and we can also apply KVL at the output side, right? But now you can see that this particular CF is there. This particular CF is in between input and output. Now, somehow we should have some expression in which the CF, part of it should come to the input part of it should come to the output. If that is coming that way, then we can represent the portion of CF at the input, we can apply KVL there, or we can apply any network related laws there. Similarly, this particular CF, if it is represented at the output, then we can apply all the network analysis laws there. That way we can independently have an expression for input and output, and we can combine them together by means of this AV itself. That is the idea here. Right now, as input and output are coupled by means of this capacitance, how do we model it, either in input or output? That is when Miller is helping us. So now, let us continue with this analysis. II can be written as I1 plus I2. Now, II is Vi by Zi, I1 is Vi by Ri. Now, what is the difference between Zi and Ri? Zi is the total input impedance considering the feedback capacitance, that is between base and collector. Whereas Ri is the input resistance of the only amplifier. So that way we can write II is Vi by Zi and I1 is Vi by Ri. What is I2? I2 is Vi minus V0 divided by XCF. We are specifically writing Vi minus V0 because we are proceeding from the input side. So these equations are very straightforward. II equals Vi by Zi, I1 equals Vi by Ri, and I2 equals Vi minus V0 divided by the reactance of the feedback capacitance, that is XCF. So using these basic equations, let us now proceed. Now I2 is Vi minus AV into Vi, because V0 is nothing but voltage gain into Vi. Vi minus AV into Vi divided by XCF. That is nothing but Vi into 1 minus AV divided by XCF. So now Vi by Zi is nothing but Vi by Ri plus Vi into 1 minus AV divided by XCF. What is this Vi by Zi? That is this II equals I1 plus I2. Let me annotate. We are expressing this equation itself. Okay. We are expressing II is Vi by Zi, I1 is Vi by Ri, I2 is Vi into 1 minus AV by XCF. So, now Vi is common everywhere. So, we can simply write 1 by Zi equals 1 by Ri plus 1 minus AV divided by XCF. So, this is the expression which we obtain by cancelling out Vi. Let me continue now. Now, let us take only this particular term 1 minus AV by XCF. Let us write it as XCF divided by 1 minus AV, just for our convenience. Now, this XCF we know it is 1 over 2 pi f into CF, right? XC is 1 over 2 pi FC, that is the reactance. So, XCF by 1 minus AV is 1 by 2 pi f into CF into 1 minus AV. So now, using this particular expression in the above equation, we can write 1 by Zi equals 1 by Ri plus 1 by X into CMI. We are purposefully using a term here called CMI, where that Mi is basically Miller. This Mi stands for Miller. So we can write CMI equals 1 minus AV into CF. You can see this equation. We have this much here, 1 minus AV into CF. So this particular term here can be represented in this manner. Okay, CF into 1 minus AV into 2 pi f is given as XCMI, or the reactance of the Miller capacitance. So where CMI equals 1 minus AV into CF. So now we have an expression with respect to input. We are representing this feedback capacitance in its counterpart at the left side. Because you can see Zi is at the left side, Ri is at the left side. Now XCMI also comes at the left side now, because it is a net effect of input impedance of the whole circuit considering the feedback capacitance and the amplifier's input resistance. So let us call this as equation 1 now. Now applying the similar conditions at the output, we can represent output in this manner now. We have this V0, we have Z0, we have R0, we have I0, I1 and I2. Now again I0 is I1 plus I2 and we have this CF here. And Z0 is the total output impedance of the network seen from the output side. R0 is the output resistance of the amplifier. So again we can write I0 equals I1 plus I2, or I0 is V0 by Z0, I1 is V0 by R0, I2 is V0 minus Vi divided by XCF. Because we are now looking at the network from the output side, we should write V0 minus Vi by XCF. Now we can write I2 as, what is this V0 minus Vi? V0 minus V0 by AV. Vi itself is V0 by AV. We are going to write this expression now starting from the output side. So let us represent input in terms of output now. So V0 minus V0 by AV divided by XCF, that is nothing but V0 into 1 minus 1 by AV divided by XCF. Or we can write now I0 is V0 by Z0. Again let me annotate. We are going to represent this expression separately now. Okay, V0 by Z0 is I1 is V0 by R0 plus I2 is now V0 into 1 minus 1 by AV divided by XCF. Okay. So proceeding this way, V0 is common everywhere. Because V0 is common everywhere, we can write it as 1 over Z0 equals 1 over R0 plus 1 minus 1 by AV into XCF. Now let us have a separate term for this right hand side, 1 minus 1 by AV by XCF. Let us write it in this manner. XCF by 1 minus 1 by AV, we know already XCF is 2 pi f into CF. So XCF divided by 1 minus 1 by AV is 1 over 2 pi f CF into 1 minus 1 by AV. Now let us use this term in the expression to write 1 over Z0 equals 1 over R0 plus 1 over X into CM0. And what is the CMO? It is not 0, it is O. Now it is the Miller's capacitance at the output side. We had found out the Miller capacitance at the input side. Now we are finding out the Miller capacitance at the output side. Now you can see that at the input side it was 1 minus AV into CF. In the output side it is 1 minus 1 by AV into CF. That M stands for Miller. So this way the CMO is nothing but 1 minus 1 by AV into CF. Now we have the counterpart of that feedback capacitance at the input side also, at the output side also. Now using these equations 1 and 2, we can slightly rewrite our network in a different fashion. Now in this case, in equation number 2, when AV is much greater than 1, then this 1 by AV is negligible. We can take AV voltage gain is always much greater in case of BJT. It will be 150, 200 times in case of BJT. So in such a case, we can simply ignore this 1 by AV. But in FET, we may not be able to ignore, because in FET the gain is 5 to 10. So it is actually much lesser. We may not be able to ignore. But in BJT, we can readily ignore. So let us consider the BJT as of now. When AV is much greater than 1, 1 by AV can be ignored, then it is nothing but 2 pi f into CF itself, seen from the output side. So we can write the equivalent network now for these expressions. See now, this is the equivalent network. You can see here, we have written the amplifier and we have written Ri, input resistance of the amplifier. Now we have written AV into CF at the input side. Why we wrote AV into CF? When AV is much larger than 1, that 1 minus AV, out of which 1 minus AV is almost equivalent to AV itself. Now you can think, if AV is equal to 200, 1 minus 200 becomes minus 199. Yeah, it is minus 199, but we will not put a minus sign here. Why? Capacitance cannot be negative. Capacitance and resistance and inductance, they cannot be having any negative values. So we are not putting any minus AV here. Instead of 199, we will take it as 200 itself. So instead of 1 minus AV, we are substituting it by AV itself. And we can write it as AV into CF at the input side. Because the expression is 1 over Zi equals 1 over Ri plus 1 over AV into CF. That is the equivalent network here. Similarly, at the output side, 1 over Z naught is 1 over R naught plus 1 over 1 minus 1 by AV into CF. That 1 by AV can be ignored because it is a very small quantity. Again, here capacitance will remain positive only. So we can write CF directly. Now look at this. Miller has helped us greatly now, because let me annotate now. We had a capacitance here. We had a capacitance connected like this. That was between base and collector, and that value was CF. Okay, that value was CF. Now, the way in which Miller helped was, instead of this particular capacitance, now we are connecting this AV into CF at the input side and CF at the output side. Now, as we had performed earlier, we can have an AC analysis for the input separately, AC analysis for output separately, and we have considered the feedback capacitance for our purpose now. Now, this is a remarkable way of analyzing circuits. That's why I'm saying Miller has helped us a lot now. You will keep on coming across this Miller throughout your engineering studies now. Maybe in future, if at all you get into circuit designs, in future, if at all you get into a particular jobs where you are involved in circuit designs, then there also you will have to remember Miller. He helped us now heavily how to represent a feedback capacitance separately at the input as well as the output. Now we can individually apply the laws of network analysis separately at the input, separately at the output. That is why this is called as Miller effect capacitance. In the next semester, you are going to study a course called Linear Integrated Circuits. There you are going to study in detail about a very beautiful circuit cum integrated circuit that is called as operational amplifier. When you start using the operational amplifier, there also using a Miller capacitance, how to have a optimized bandwidth or how to have a optimized phase response, you are going to study that in future. That's why I'm telling you, Miller has contributed a lot for our circuit analysis now. Now, this was the effective network for the common emitter configuration. Now, for common base and common collector configurations, the Miller effect capacitance is not a concern for high frequency applications. Can anybody tell me why? For common base and common collector configurations, he says the Miller effect capacitance is not a concern. Can anybody tell me why? You will have to visualize the common base and common collector configurations, and then you will have to understand this. Can anybody tell me? I have 33 students here. I hope all of you are listening. At least make an effort. Why in the common base and common collector configurations, this Miller effect capacitance is not a concern? You can put your answer in the chat box also. I am waiting. Okay, nobody is making an attempt. Let me tell you the answer. You have to visualize the common base now. Let me write the common base circuit. Common base will be like this, right? Where base is grounded. Base is grounded and input can be given at the collector and output can be taken at the emitter. Now this is common base. Now in case of common base, there is a N region at the collector, P region at the base, N region at the emitter. Now between base and collector there is a junction capacitance. Again between base and emitter there is a junction capacitance. Now base is grounded. So there is no capacitor between emitter and collector. Even if it is there as a stray capacitance, its value is very less. Why? Because there is no direct connection between emitter and collector. Junction exists only between base and collector. Junction exists only between base and emitter. Junction does not exist as such directly in between collector and emitter. That way, we cannot represent between a collector and emitter, we cannot represent it as a single capacitance. Anyhow, if there are two capacitances, both capacitances, two ends are connected to ground itself. That is how in common base configuration, the Miller effect capacitance is not a concern. Fine. What about in the common collector configuration? In the common collector configuration, we have like this, and the collector is AC ground, and at the base we have input, and at the emitter we have output. Okay, and at the emitter we will have resistance, and here it is ground. Now why is it that even in common collector configuration the Miller effect capacitance is not a concern? Now look at this, we are giving input at the base, we are taking output at the emitter, collector is grounded. That means if at all you have a capacitance between base and collector, collector other end is anyhow going to be grounded. It is not going to affect our output. As far as the emitter junction is concerned, this is a forward bias junction now. This is a PN junction which is now forward biased. When it is forward biased, you know that in the forward bias condition, again the capacitance is of a negligible value. Only when the PN junction is reverse biased, it will pose a larger value of capacitance. When it is forward biased, that particular capacitance can be ignored. Now for this reason, both in common base and common collector configurations, the Miller effect capacitance is not a concern, especially for the high frequency applications, because those stray capacitances are also negligible. Whereas in common emitter, we cannot ignore it because base to collector junction is reverse biased there. That is the reason. Now can anybody tell me what happens effectively with the Jfet? Let me admit a student who is waiting. Can anybody tell me what happens effectively with the Jfet now when compared to BJT? Only thing is in Jfet, we may not be able to ignore that 1 by AV there. We may have to consider that 1 by AV because AV is very less in case of Jfet. That 1 minus 1 by AV also cannot be ignored, and that 1 minus AV at the input side also cannot be ignored. For the BJT, we can write it directly this way, AV into CF, and here we can write directly into CF. Now for a Jfet, let me stop annotating, let me start fresh. For a Jfet, we will have to write 1 minus AV into CF, which we are going to do later on. And for this CF, we will have to write CF into 1 minus 1 by AV. Okay. I am crudely writing this because I am writing through mouse only. CF into 1 minus 1 by AV, where in case of Jfet, that cannot be ignored. Now my question is, for those who are listening to me, the question is, in Jfet, just like we have a common emitter configuration in BJT, we have a common source configuration in Jfet. There also, between gate and drain, that junction is reverse biased. Please visualize that pinch off region and visualize the structure of the Jfet, which I had shown earlier in a three-dimensional way. So that gate to drain region or gate to drain junction itself is reverse biased. So just like in common emitter configuration of BJT, even in the common source configuration of Jfet, we will have the same type of Miller effect capacitance. The only difference is we will not ignore that 1 minus AV, we will not ignore that 1 minus 1 by AV. Now my question for the students who are listening to me, the question is, what happens in case of common gate and common drain configurations? At least I am hoping someone will answer my questions either in chat box or by unmuting. Okay, no one is responding. Our students are highly talkative when it comes to all other subjects. When it comes to their own subjects, they don't talk. That is the problem with not only our students, that is the problem with every student, I should say. Fine. Anyhow, as you are not telling, I only have to tell. Let me tell. Just like common base, now we have common gate. In the common gate, just visualize the FET in the common gate, where gate is grounded, input can be given at the drain, output can be taken at the source. Now in that case also, between drain and source, there is a channel that is existing. Remember, FET is normally on and you are turning it off by applying a negative gate bias. Please remember that. Whereas BJT is normally off, you are turning it on by supplying base current. Now in case of Jfet, when gate is grounded, between drain and source, there is a direct channel, right? There is no junction at all. Between drain and source, there is no junction at all. There is a direct connection because it is a single semiconductor. Unlike BJT. In BJT, you have collector to base and base to emitter. But in Jfet, it is direct connection between drain and source. So there is no capacitance there at all. There is only a channel's resistance. That is in case of common gate. What about common drain? Now in case of common drain, what happens there is between gate to source. What is that particular capacitance? Between gate to source, that is going to be a forward bias junction. So in such a case, again the Miller effect capacitance is not a concern. Anyhow, we are not dealing much with common base and common collector configurations or common gate and common drain configurations because they are special purpose amplifiers. You already know that common collector and common drain, their signals gain or voltage gain is unity. So we are focusing more on common emitter and common source configurations. Okay, with this coverage of Miller effect capacitance, let me proceed now to the discussion of high frequency analysis. If at all you have any questions till now, you can ask me, or else I will proceed because I am anyhow a talking parrot. Till 2:45, 2:50, I keep on talking. hoping that you will keep on listening. Fine. Let us discuss the high frequency response. Let us consider the BJT amplifier first. Now you can recall in our low frequency response, we discussed a network, CR network, capacitance first, then resistance next, because we have been seeing it from the input side or even in the output side when there was an input resistance and there was a capacitance. Now in case of a high frequency response, we have these parasitic capacitances which are internal to the device, and signal gets leaked through these capacitances. Signal may go to ground because of these capacitances, or signal may go to output directly without passing through the switching action of the transistor. So for a high frequency response, we have to deal with the RC network now. For low frequency response, we analyze the CR network. Now we will discuss the RC network, where you can see here R and C is there. Now FH occurs when XC equals R. This we had discussed earlier. Whenever resonance occurs, when our reactance equals resistance, then the high frequency cutoff will occur, which means X equals 1 over 2 pi into FH into C, that is equal to R because of the resonance. So we can write now FH equals 1 by 2 pi RC. In the same way we had written earlier that FL equals 1 by 2 pi RC. The only difference is that the models of R and C are in opposite directions now. So FH equals 1 by 2 pi RC. Now let us write an expression for the voltage gain. AV is V0 by Vi. We are writing the gain for this particular network now. Now don't think that we are writing the voltage gain for the amplifier. We are writing it for this particular network now. So V0 by Vi is nothing but minus Jxc divided by R minus Jxc. Why? We are measuring the signal across the capacitance. So naturally, the reactance of the capacitance is modeled here as minus Jxc. Okay, now I remember I had asked you a question about why we use J. I had asked this question 2 or 3 classes before. Did you find out any answer? Did anybody find out the answer that why are we using this J or I, which is basically imaginary, when it is square root of minus 1? When that square root of minus 1 does not exist, why are we using it in all our analysis? Something which is imaginary, why it should come into our mathematical analysis? Anybody has found out? Okay. Sayan has typed an answer because the reactance is lagging compared to the resistance. Okay, if the reactance is lagging in compared to the resistance, we can put a minus sign in the phase angle, right? When we calculate the tan inverse of FL by F or FH by F or whatever, then we can simply write minus 45 degree, minus 90 degree. But here J is a term which is square root of minus 1. When J is square root of minus 1, okay, Rohit is putting an answer that to obtain it in the rectangular form. Okay, rectangular form is as per the Cartesian coordinates. But again, my question is, whether it is a rectangular form, whether it is a polar form, my basic question is, when J equals square root of minus 1, square root for negative number does not exist, then why are we using square root of minus 1? That is the question. Later on, because we started using that square root of minus 1, we can represent either in the polar form or in the rectangular form, in which form. Those are different flavors of mathematics. But the very first question is, why do we consider square root of minus 1? Again, Sayan gives an answer, because we don't consider the effect of reactance. No. We are considering the effect of reactance. Without considering the reactance, how are we doing circuit analysis? Everywhere we have considered XC here now. So we are considering the reactance. Anyway, I'll give you time. This is a very fundamental question. Many times for the fundamental question, people don't have answers. Actually, there is an answer. There is a definite answer. But that answer is not there in the textbooks at all. Many times textbooks miss all these fundamental concepts because textbooks write the books for a given course or a given subject. So they will presume that these fundamentals are already covered in some other previous course. But as it was not covered anywhere, they will omit it out or leave it out. So I'll give you time. At least in the next class, you find out and tell me. You ask Googleshwar. That is what I do also, right? Ask Googleshwar. Googleshwar knows everything. So ask Googleshwar, find out and tell me the exact answer for why do we use square root of -1. This is a fundamental question and there is a distinct answer. Next class at least, if I don't remember this, you remind me and tell me the answer. So let me proceed. AV equals V naught by Vi. We represent it for this RC circuit as minus JXC divided by R minus JXC. Let me rewrite this particular expression in this way. 1 by 1 minus R by JXC. The same way which we did for the low frequency analysis network. So now, substituting for this XC itself, it becomes 1 by 1 plus J into R into 2 pi Fc. That XC becomes 1 over 2 pi Fc, and instead of J at the denominator, we can write J at the numerator by changing the sign. Because you know that J square is nothing but -1, right? J equals square root of -1. So J square is -1. So we can write that J at the top. 1 minus 1 by J becomes 1 plus J. And Xc becomes 2 pi Fc, 1 over 2 pi Fc, 2 pi Fc comes to the numerator. So you can see this AV equals 1 by 1 plus J into R into 2 pi Fc. Let us use this further. Now using that equation 1. Equation 1 was what? Equation 1 was Fh equals 1 by 2 pi Rc. Now using that, we can write AV equals 1 by 1 plus J into F by Fh. Earlier we had that 1 by 1 plus J into FL by F, if I remember it correctly. I don't know whether I have remembered correctly or not. You can verify later on. Now this is AV equals 1 by 1 plus J into F by Fh. That is equation number 2. Now we can write this in the magnitude and the phase form as a standard expression. We can write it as AV equals 1 by square root of 1 plus F by Fh whole squared into the angle is tan inverse of F by Fh. As we did in the previous analysis, we can proceed in the same manner for plotting Bode plot. Bode is our favorite scientist now. So using the same methodology, we can have the writing of the Bode plot. So when F equals Fh, mod of AV is 1 over root 2. This is already being discussed earlier many times. So now as earlier, this results in a high frequency plot with the reduction of minus 20 dB per decade or minus 6 dB per octave. Please recall that decade is either multiplication or division by 10 and octave is either multiplication or division by 2. We had seen this earlier where our ideal Bode plot will have a roll off of 20 dB per decade or 6 dB per octave as per our calculations only. Why minus sign? Because it is reducing from the maximum gain. So we put a minus sign. That's why we call it as roll off. It is rolling down. Now using this particular analysis, we can write a high frequency equivalent model for the transistor or for our amplifier circuit. You can see this now. This is a BJT common emitter amplifier, and here you can see it is a voltage divider bias network where you can see a signal source along with the source resistance in series. Then we have this R1 and R2 for DC biasing, voltage divider network. Then we have RC at the collector, and emitter is directly connected to ground because of the bypass capacitance. It is not explicitly shown here. We always use a very large value of bypass capacitance at the emitter. So as far as this particular circuit is concerned, for high frequency analysis, we need not write that RE and CE. The reason is CE is going to short RE when there is a high frequency. You know that X equals 1 over 2 pi Fc. When F is much larger, Xc will be much lesser. That is why I have written emitter directly connected to ground. And then at the output we have the load resistance. Apart from that, you can see some other strangers here. You will see CBC, CBE, CCE, and you will also see CWI, CWO. Now what is this CBC? Base to collector junction capacitance. CBE, base to emitter junction capacitance. CCE, collector to emitter capacitance. It is not a junction capacitance now. It is a net effect of CBC as well as CBE if it is taken that way. Otherwise, it can be a net effect of the complete device from collector to emitter. That way we can represent CBC, CBE and CCE. Now what is the CWI and CWO? Can anybody tell me? It is not Miller capacitance. We have not yet modeled the circuit with the Miller capacitance. We are going to use the Miller capacitance for this CBC later on. Because emitter is grounded, we are going to use a Miller effect here. But what is the CWI and CWO? Fine. As usual, our students are silent, so I am a talking parrot. CWI stands for the wire capacitance at the input, and CWO stands for the wire capacitance at the output. Whenever we connect the signal source to the transistor, in between we have a copper wire. Whether it is a discrete circuit or whether it is an integrated circuit, even inside the integrated circuit, there is a metal wire. So, even at the input you have a wire, even at the output you have a wire. Now, with respect to wire, there will be always a ground wire with respect to any wire. Now, in between the main wire and the ground wire, there is always a capacitance because all wires will have insulating sheaths. All wires which we use are protected by a insulating plastic sheath. So that plastic sheath is acting like a dielectric medium. Even inside the integrated circuits, we have insulators in between two metal layers. So there also the capacitive effect is there. So when there is a capacitive effect, wherever there is a wire, there is a capacitance. From the input side, if we model that wire, we have to write a capacitance with respect to ground. Similarly, at the output also, we will have to model that with respect to ground. Now, using this particular circuit diagram, in the next class, let us perform a high frequency analysis for our common emitter BJT amplifier. So, see you in the next class. In the next class, I expect that at least one of you will give me the correct answer for why are we using square root of -1 in our mathematical analysis. So, see you in the next class. Take care and goodbye.